How do we actually know the Earth is 4–5 billion years old? I've always just assumed this is true because people smarter than me said so. Lately I've been wondering what the methods are that they use to determine the age of the Earth. Note I'm not looking for a two-word explanation like carbon dating. How does it actually work? Is it not affected by different environments, and are we not just extrapolation data to come to a not very reliable conclusion? Of course the numbers scientists got are still an estimate, but why is it, in the science world, widely accepted? The primary method used to measure the age of the Earth is radiometric dating, of which radiocarbon dating is one method. But radiocarbon is not in any way relevant for the age of the Earth because the half-life of C14 is way too short. Radiocarbon can reliably date things back to approximately 50,000 to 60,000 years. All radiometric dating relies broadly on the same principle, i.e., particular unstable radioactive isotopes decay to particular stable isotopes at a known and measurable rate, e.g., uranium-238 decays to lead-206 with a half-life of 4.47 billion years, meaning that in 4.47 billion years, half of the starting U-238 in a given sample has decayed to lead-206. Thus, by measuring the ratio of a particular parent isotope to child isotope and knowing the decay rate, which is related to the half-life, we can use the age equation to determine the age of a sample, within an uncertainty based on a variety of things like our ability to measure the ratio, etc. The effective age range of a particular geochronometer, like U-238 to Pb-206, depends on its half-life. Decay systems with very long half-lives, several billion years, are very good for measuring things like the age of the Earth because there are still measurable amounts of both parent and child even after billions of years. In contrast, the same decay systems are not appropriate for dating young things because there has been so little decay that it's challenging to measure the presence of any child isotope. Dating young material is where decay systems with comparatively short half-lives, like radiocarbon, would be much more useful. The converse is also true though, i.e., radiocarbon is useless for dating the age of the Earth because with an approximately 5,700-year half-life, beyond approximately 60,000 years, there is no measurable parent isotope left, and thus the only thing we can say is the sample is older than approximately 60,000 years. Beyond that level of explanation, there are lots of nuances to radiometric dating and likely follow-up questions, but I'll refer you to our FAQs on radiometric dating for some of the more common forms of those, e.g. 1. Do we need to know how much radioactive parent there was to start with? 2. What is a date actually dating? And 3. How do we interpret a date for a particular rock? With specific reference to the age of the Earth, it's important to note that we generally are not dating Earth materials themselves to establish this age. The reason for that is largely because of plate tectonics, i.e., the age of all of the material at the surface of the Earth reflects the age that given rocks and minerals formed through various tectonic and igneous processes after the formation of the Earth. Thus, dating material from the Earth would only get us a minimum age for the Earth, i.e., the oldest age of any Earth material, which at present is approximately 4.4 billion years for some individual zircon crystals, would still be younger than the total age of the Earth. This is why we use radiometric dates of meteorites to date the age of the Earth, and really, it's to date the age of the formation of the planets in the Solar System. Effectively, many meteorites are pieces of early planets and planetesimals that formed during the initial accretion phase of the protoplanetary disk, and the radiometric dates within crystals within these meteorites, or in some cases bulk rock ages, reflect the timing of their formation, i.e., when planets were beginning to form. We have dated many different meteorites by several different methods, e.g., most commonly PBPB, but also ARAR, RIOS, and SMND, and broadly speaking the ages of these meteorites have generally been similar to each other within the uncertainty on the ages, which is consistent with the hypothesis that ages of meteorites should 1. Be broadly similar and 2. Should reflect the timing of formation of the planets. Finally, it's worth noting that when we talk about the age of the Earth, we're assigning a single age to an event, i.e., the accretion of material to form the Earth, or the other planets, etc., that was not instantaneous. Thus, the most accurate way to think about the 4.54 billion-year figure for the age of the Earth is that this is the mean age of accretion and/or core formation of the Earth. Edit I'm locking this thread because virtually every follow-up question is already addressed in the FAQs that I linked above.